let us have a brief introduction about the matrices and determinants. A matrix is a rectangular arrangement of numbers into rows and columns. Matrix. Generally, we denote the matrix with the help of a 2 suffixed notation. Here, Aij would mean, it's abbreviated in the form of representation of the matrix. I ranges from 1 to m, that is, we write like this: A1 1, A1 2, so on, A1 n, A2 1, A2 2, so on, A2 n, AM 1, AM 2, so on, AM. This has m rows. Row is this. How many rows are there? The first suffix is pointing to the row position, and second suffix, as you see, is pointing to the column position. This is column 1. This is column 2. Row 1, row 2. So we have column n, column row m here. So this is a m rowed n column matrix here. Example of we'll give one simple example. A 2 by 3 matrix. Suppose I want a 2 by 3 matrix. A is a 2 by 3 matrix. So let's write something. So 2 rows and 3 columns we have to write. 1 3 5 2 4 minus 3, something like this. This is a 2 row 3 column matrix. We have matrices which are square matrices. Square matrix is a square matrix in which the number of rows and columns are same. Number of rows is equal to number of columns. Okay. Just as we perform addition of real numbers, we can add addition of vectors for that matter. We can add 2 matrices. We can subtract a matrix from another matrix of the same type. Same type in the sense number of rows and number of columns of both the matrices should be same. Right. Suppose A and B are similar matrices, meaning they are of the same, they have same number of rows and same number of columns. We can perform an operation A plus B, that is, we add corresponding elements. If you want to subtract A minus B, you want to perform A minus B, you will subtract the corresponding elements there. Okay. Now let us move on to the types of, let's move on to the types of square matrices. Types of square matrices. A square matrix is said to be triangular, is upper triangular, if and only if all the elements below the principal diagonal, this is called the principal diagonal, these are all zeros. That is, we'll put it this way, what is this? If I represent it this way, for example, we'll have 0 0 0 1 2, anything here 0, anything here, and anything here. That is, elements below the principal diagonal entries have to be zeros. Okay, so how do you put it? We say Aij is upper triangular if and only if for Aij is 0 for all I less than j. So let us look at some problems on matrices and determinants. The problem problem number 1, question number 1 there. If A and B are square matrices of order 3 by 3, A is an orthogonal matrix and B is a skew symmetric matrix, which of the following statements is not true? First statement is determinant of A is equal to plus or minus 1. determinant of B is 0, determinant of AB is 1, determinant of AB is 0. These are the 4 statements. There are 2 types of matrices we are talking about. A is orthogonal matrix. A is orthogonal matrix. So, what is the definition of orthogonal matrix? A into A transpose must be equal to A transpose into A, and that must be equal to I. That is, A transpose and A will be the inverses of each other. Okay, what is it you can say about the determinant of an orthogonal matrix? Now let us apply determinant both sides. Determinant of A into A transpose is equal to determinant of I. What is determinant of an identity matrix? 1. But what is determinant of the product of 2 matrices? Determinant of the product of 2 matrices, product of the determinants, and that's equal to 1 here. But we also know that determinant of A transpose is equal to determinant of A. Therefore, this becomes determinant of A into determinant of A, det A square. So this gives me that det A has to be is equal to det A has to be plus 1 or minus 1. So first statement has to be true. Now we are interested in the statement which is not true. Okay, now let's look at what is given about B. What is given about B? B is skew symmetric matrix. That's what we are given. Matrix of order 3. We know that every skew symmetric matrix of odd order has to have its determinant to be 0. So 3 is an odd number, therefore determinant of B is 0. Now, so obviously we have determinant of A to be plus or minus 1, determinant of B to be 0. So determinant of AB has to be 0. What is determinant of AB? Det A into det B. So one of them is being 0, we should have the determinant to be 0 there. Therefore, obviously the option 3 is not correct, and hence the correct answer is 3. Now let's move on to the next question, question number 2. If A is a 3 by 3 matrix and determinant of A is not equal to 0, adjoint of A is equal to det A square into A, first option, det A into A, third option being A by determinant of A, fourth option being A by determinant of A square. Now, what is first of all adjoint of a matrix? Adjoint of a matrix is transpose of the cofactor matrix. This is the transpose of the cofactor matrix. Of cofactor matrix. One important property of this is that A into adjoint of A is equal to determinant of A into I. From here, it's clear that A inverse will be equal to adjoint A by determinant of A. Because A operated with adjoint A by determinant of A, you bring this determinant of A down. So A multiplied with the adjoint A by determinant A will give me identity matrix. So that means that this has to be the inverse. And this also would imply that adjoint of A inverse is equal to, now adjoint A with what matrix if I multiply, do I get an identity matrix? I bring this determinant of A, bring it down here, that's going to be 1 by det A into A. Adjoint of A inverse is equal to this. Now this is an important result that we will be using here. Now we apply determinant both sides. Apply determinant both sides. Determinant both sides. So when you apply determinant both sides, determinant of the product of matrices is product of the determinant. So we get det A into determinant of adjoint of A is equal to Now this is determinant of det A into I. What is that going to be? Det A raised to the power n. I mean, assuming that A is a n by n matrix. Assuming A is n by n matrix. A is n by n matrix. I am mentioning this because this is a general result that we are using. So what we have is det A into I. So every entry in the, it's a scalar matrix wherein all the entries of the principal diagonal entries are det A's. So when you open up the determinant, it will be product of the principal diagonal entries. So det A multiplied n times det A power n. Now determinant of adjoint of A is equal to det A raised to the power n minus 1, because I can bring it down here. So this is another result that is very important here. A into adjoint of A is det A into I. Determinant of adjoint of A is equal to det A to the power n minus 1. Okay, now what we wanted was adjoint of A. Now adjoint of A. What do you know about adjoint of a matrix here? Adjoint of a matrix is, so instead of A we will write adjoint of A. What is that equal to? We can write that as A inverse into det A. From here adjoint of A is equal to det A into A inverse. A inverse. Okay, so instead of A here we have adjoint of A. So that I should write it as determinant of adjoint of A into adjoint of A the inverse. But what did you know about, what do we know about adjoint of A the inverse? A by det A. So let's write that. What do I know about adjoint of A, determinant of adjoint of A? Det A to the power n minus 1. So that makes it det A to the power n minus 1, and here we have A by, okay, so this is your adjoint of A, that is det A to the power n minus 1 into A by det A. So that makes it det A to the power n minus 2 into A. Okay, now this is a generalized result that you can bear in mind. Now so adjoint of A is equal to det A to the power n minus 2 into A. This is an important result that should be borne in mind. Now in our problem n is equal to 3. It is A is a 3 by 3 matrix. So n has to be 3. Therefore since n is 3, we have adjoint of A to be equal to det A power n minus 3, n minus 2, that will make it det A into A. So the right option is answer 2. Answer is 2. Now if A is a 3 by square matrix, so that A into adjoint of A is equal to the diagonal matrix KKK, then determinant of adjoint of A is equal to 1 K, 2 K square, 3 K cube and 4 K power 4. It's evident that A has to be a 3 by 3 matrix because on the right hand side we are given a diagonal of KKK. That means a diagonal matrix KKK would mean the diagonal entries are KKK. It is this matrix. And rest of the entries are all zeros. Right? Now A into adjoint of A, diagonal matrix KKK is equal to matrix represented by this. It's a 3 by 3 matrix, scalar matrix with all the scalars along the principal diagonals entries are equal to K. So I can even write this as K into I. I being a 3 by 3 identity matrix. Now what do we know about A into adjoint of A? He has given that to be K into I. But what do we know about A into adjoint of A? This is nothing but det A into I. So det A into I is K into I. So what would have been det A? This implies det A must be equal to K. See, we know that A into adjoint of A is equal to determinant of A into I. So determinant of A is K. That's what we could conclude. And we also know that determinant of adjoint of A is equal to det A to the power n minus 1, where n is the order of the matrix A. But here, what is the order of the matrix A? It's 3. So we have det A to the power 3 minus 1. That makes it det A square. Okay, so the answer is, but what is det A? K. So answer is K square. Therefore, the right option is, answer is 2. Let's, question number 4. If AB is equal to A and comma BA is equal to B, then we have 3 statements. First statement reads A square B is equal to A square. Second statement reads ABA is equal to A, comma BAB is equal to B. Third statement says A square is equal to A. Now what are we given? We are given that AB is equal to A and BA is equal to B. This is given. So from this, as the hypothesis, can we conclude these 3 statements? This is what is the question. So now the question is, let's see, how do I write what is A square B? A square B is nothing but A into AB. Matrix multiplication is associative, so this A I can associate, this A and B can be associated. So what we have is, but what is AB? We know that AB is nothing but A. So that makes it, in place of AB here, I am going to replace it with A. So what we have here? A into A, and that's equal to A square. So A square B is equal to A square. That is, option 1 is okay. Option 1 is okay. Now let's move on to this. ABA. Let's consider ABA. What is ABA? A into this BA part, I can write it in the form of, we will club this B and A. So BA. What is BA given to be? B. So let's substitute AB. Let's substitute in place of BA, B there. And what is AB? Again, A. So ABA is equal to A. So this is also, this part is correct. Similarly, we can also conclude that BAB is equal to B. So this is true. Now coming to A square equal to A, is this true or not? How do you write A square? What is A square for us? A is AB. So AB multiplied with AB. But what is this? We can use matrix multiplication being associative. We can associate, club this B, the middle 2 matrices, BA and then B. But what is BA? B. So here we can write this inside the bracket, we will replace it with B and then we have a B. Now let us club these 2 matrices AB and write this as AB into B. So without changing the order of the multiplication of matrices, we know that we can group them under multiplication. So grouping, I'm grouping A and B now. This first matrix and second matrix. What is AB? A. Get back. What is AB? A. So A into B. But what is again AB? A. Where did we start with? We started with A square and we ended up with A. So A square is equal to A there. In fact, by symmetry, you can also conclude that B square is equal to B. That is of course not asked, but anyway, we can conclude. We can even conclude B square equal to B. So in this problem, it is mainly this hypothesis is given, and the manipulation is just purely based upon one law of multiplication of matrices being associative. That's the only thing that we have made use of here, and clearly the answer is that all the three options are correct. Therefore, answer is 1. Answer is 1. Okay, question number 5. So let's move on to the question number 5. Matrix A is such that A square is equal to 2A minus I, where I is a unit matrix. Then for n greater than or equal to 2, A power n is equal to what? Na minus n minus 1 into I, 2 Na minus I, 3 2 power n plus 1 into A minus of n minus 1 into I. Fourth option, 2 power of n plus 1 into A minus I. Here actually we can just put n equal to 2 and verify which of the forms are holding good. That is, clearly when n is 2, we have A power 2 to be 2A minus 2 minus 1 into I. That is the first option there. Second option will not satisfy that. Second option will mean that A square is equal to 2A minus A. First and second option appear to be same there. So shall we move on and look for n equal to 3 and see which formula can hold good. So then now there is it appears that it could be either 1 or 2. So let's verify. What is that? A cube. Let's go for A cube. What is A cube? A square into A. But what is A square? We know 2A minus I. So 2A minus I into A. What is that again? 2A square minus A. But what is A square again? 2A minus I. So 2 into 2A minus I minus A. So what does that make it? 4A minus A, that is 3A minus 2I. 3A minus 2I. So observe that when n is 3, it appears that A power n equal to Na minus of n minus 1 into I appears to be the more appropriate option here. And let's verify if for A power 4 also. Verification, A power 4. What is A power 4? A cube into A. But what is A cube? We have just now found 3A minus 2I. So 3A minus 2I into A. But what is that? 3 into A square minus 2A. What is A square, by the way? A square was given to be 2A minus I. This is given. This was given already. So we've been using that repeatedly. 3 into 2A minus I minus 2A. So what does that make it? 6A minus 2A. That makes it 4A. And we have minus 3I. Again, it obeys this. When n is 4, we have 4A and 4A minus of 4 minus 1 into I. So it appears that by induction we can conclude that we can actually prove that A power n is equal to Na minus n minus 1 into I. So what we have done was we have actually put in n equal to 2, and first option and second option were both coming out to be same. So there may be a tie between these two options. So we broke the tie. That is, we put n equal to 3, we put n equal to 4 and verified which of the formulae is going to be more appropriate, or in fact is correct. So answer is 1. Okay, let's move on to the next question, question number 6. Here, if A is equal to ABCD and then I is equal to the identity matrix 1 0 0 1, A square minus A plus D into A minus of BC minus AD into I is equal to 1 0 2 I 3 2I 4 A minus D. Now first of all, fourth option is ruled out because it is involving matrices and A minus D is a number. That can't be true. A is a 2 by 2 matrix. Entire equation will have to yield a 2 by 2 matrix, but that's not the option 4. So it may be option 1 or 2 or 3. Now look at this. We have for a 2 by 2 matrix, A is a 2 by 2 matrix, which is in the form of A is equal to A, B, C, D. Then we have a result. The result says A square minus trace of A into A plus determinant of A into I is equal to null matrix. Null matrix. What is a null matrix? Matrix with all the entries being zeros. So null matrix of what order? Same as the order of the A, that is 2. 2 by 2 null matrix it is. What is trace of A? A plus D. So that is A square minus A plus D into A plus, what is the determinant of this matrix A? AD minus BC. AD minus BC into I is equal to 0. Now that is clearly what is given. A square minus A plus D into A minus of BC minus AD into I. That is equal to what? Null matrix here. Null matrix here. So the right option here is answer 1. The result is that we have made use of this result. That is, if A is a 2 by 2 matrix, this equation is always true. It can be easily verified from just simple matrix multiplication and addition is involved here. Easily it can be verified. So A square minus trace of A into A plus determinant of A into I equal to 0, null matrix is a result. So let's move on to the next question, question number 7. Let's move on to the next question, question number 7 here. Now this question is an assertion reasoning type. We have two statements A and R. We got to see whether both the statements are correct and one is the correct explanation for the other or not. Now the first statement reads like this: A is equal to, the first statement A is AB is A and BA is equal to B. That implies A power n plus B power n is equal to A plus B. The reason R says AB is A and BA is B, then A and B are idempotent matrices. So which of the following options are correct? Both A and R are true and R is the correct explanation to A. Both A and R are true but R is not the correct explanation to A. A is true but R is false. A is false but R is true. Now let us look at this here. What is given in the first statement? Statement A tells us AB is equal to A as well as BA is equal to B. And what is the conclusion that is being drawn? A power n plus B power n is equal to A plus B, where n is any natural number. Okay. Here, let's observe one thing. What is A square? We can write it as AB into AB. And what is that? We can associate BA into B. But what is BA? That is nothing but, BA is nothing but B. So A, B, B. But what is AB? Again, let's associate these two. It is AB to B. And what is this AB? This AB is nothing but A. So again AB. So we have AB, which is nothing but A. So we started with A square, we ended up with A. Similarly, B square is also B. Now, if A square is A, then the matrix A is said to be idempotent matrix. Implies A is idempotent. That is a condition for idempotency. idempotent matrix. Okay. So from the from AB equal to A and BA equal to B, we are able to clearly see that A and B are both idempotent. B square is B and A square is A. So second statement is clearly true. Now what about the first statement? Can we say that A power n plus B power n will be equal to A plus B? If A square is A cube will also be A. What is A cube? A square into A. What is A square? A into A again. But what is A into A? A square. A square is A. So A cube is A. Now so on, we can conclude that A power n is equal to A. Inductively, we can go on and to conclude that A power n is equal to A. Similarly, what you have done for A is also true for B. There is a symmetry in the given equations. So B power n is also equal to B. Therefore, clearly A power n plus B power n is equal to A plus B. Clearly, this is true. So we observe that both the statements A and R are correct, and R can be taken as the explanation for A. So answer is the first option. Answer is the first option. Question number 8. Now if A, B, C are all positive and not all equal, not all are equal, then the value of the determinant ABC, BCA, CAB is 0, less than 0, greater than 0, cannot be determined. Okay. Now this is a determinant where you see that there is a cyclic order maintained in the entries here. ABC, BCA, CAB. That's the third row. Now this determinant is a standard determinant that is given by 3ABC minus A cube plus B cube plus C cube. You can easily open it up and observe that this is it. And this we know it can be factored out as minus of A plus B plus C into A square plus B square plus C square minus AB minus BC minus CA. We can write like this. And we know that this is the second part is definitely positive. What about the first part? ABC are given to be positive numbers. So this part is positive. Minus of a positive quantity. This is positive. What about this? This is clearly a positive quantity. It is half of A minus B whole square plus B minus C whole square plus C minus A whole square. This we know. This entire expression is half into this thing. Half into this thing. Now that half into A minus B whole square plus B minus C whole square plus C minus. ABC, out of ABC, at least two of them are not equal. So this will be definitely a positive quantity. This is a positive quantity. When can this be? This is always actually non-negative. When can this be 0? When all of them are equal. But you are given that at least that not all are equal. That is, at least one pair of the numbers are unequal. Therefore, this part has to be positive. So positive into negative. So that makes it negative here. The entire expression is negative. So we have the determinant to be negative here. So answer is 2. Answer is 2. Okay. So next question. Question number 9. Determinant of the matrix 0 P minus Q, P minus R in the first row, Q minus P 0, Q minus R minus P, R minus Q 0 is P minus Q into Q minus R into R minus P. Second option 0, third option PQR, fourth option being 4 into PQR. Now clearly we observe that this is in the form of the principal diagonal entries are all zeros. And suppose you have an x here, you have a minus x here, and you have a y here, you have a minus y here, and you have a z here, and you have a minus z here. That is, if you see Aij is equal to minus Aji for all ij. This is the condition that is being satisfied by the matrix whose determinant we are trying to find out. So that type of a matrix we know is a skew symmetric matrix. So the given matrix is skew symmetric matrix of what order? Of order 3. Now that is 3 is an odd number. Determinant of a skew symmetric matrix of odd order. Skew symmetric matrix of odd order is equal to 0, we know. So the right option is 2. Answer is 2. So let's move on to the next question. Question number 10. The determinant x minus 2 whole square, x minus 1 whole square, x square, x minus 1 whole square, x square, x plus 1 whole square, x square, x plus 1 whole square, x plus 2 the whole square is equal to what? Now if you see that the 4 options, first option is 8, second option is 16, third option is minus 8, fourth option minus 16. Now the determinant is independent of the x value. So meaning it's a kind of a constant. Okay, so the x terms would cancel after expanding. So what is it you can say? It has to be a constant function kind of a thing. So it should yield the same value for all values of x. So what we'll do is we will give in some value, a simple value for x. I'll put x as 0. Put x as 0. Now we have to be careful in doing so. I could do this because all the options were independent of x. So no matter what may be the value of x, we will always be getting the determinant value to be some constant number. So we could substitute some value. Why 0? Anything we can do, but that will make most of the entries 0. Therefore, that's why we are using x equal to 0. So when I use that, I'll get determinant for 0 minus 2 the whole square, that is 4. I get 4 here. I get 1 here, and I get a 0 here. I get a 0 here, 0 here, and 1 here, and again 1 here, 1 here, and 4 here. So when you open up this determinant, it comes out to be equal to minus 8. So the answer is 3. So the key lies here that it is all the options being independent of x. I can put some value to x and find out. So let's move on to the next question. Question number 11. Question number 11. If dr is equal to the determinant 2 power r minus 1, 2 into 3 power r minus 1, 4 into 5 power r minus 1 in the first row, x, y, z in the second row, third row having 2 power n minus 1, 3 power n minus 1, 5 power n minus 1, summation of all the determinants sigma dr are ranging from 1 to n is first option 2 power n into 3 power n into 5 power n, second option 2 power of n minus 1 into 3 power n minus 1 into 5 power n minus 1, fourth option is xyz, third option for xyz, fourth option 0. Now let's make an observation here. We are given dr to be the determinant 2 power n r minus 1, 2 into 3 power r minus 1, 4 into 5 power r minus 1, xyz, 2 power n minus 1, 3 power n minus 1, 5 power n minus 1. Here we are interested in sigma dr are ranging from 1 to n. Sigma dr are ranging from 1 to n. So summation of these determinants is what we want. This is what we want. Now we make use of this property of determinants. The property of determinants is this. Suppose you have in one row something like A plus X, B plus Y and C plus Z, and alpha, beta, gamma. Okay, capital A, capital B, capital C, some numbers like this. We can split this determinant into two determinants by the first row. We can write it as keeping the other two rows as it is, alpha, beta, gamma, ABC, alpha, beta, gamma, ABC. We will write now in the first row, first A, then B and then C, and in the second determinant we're going to write X, Y, Z. Now it's not only true for two numbers being added up in a particular row. Every entry is, now when you have three numbers like this, suppose you have some X dash and Y dash and some Z dash, then we'll have one more determinant, keeping the other two rows as it is, ABC, and we'll have X dash, Y dash, Z dash. So this can be carried over for any number of determinants. So what we are doing is, now let's look at it this way. We have a summation of, in this determinant only this row is a variable row. So I can look at this as summation of these determinants can be viewed as summation in one particular row. So I can rewrite this as sigma 2 power r minus 1, r ranging from 1 to n, and then this entry will also be 2 into sigma 3 power r minus 1, r ranging from 1 to n, 4 into sigma 5 power r minus 1, keeping the other two rows as it is. So what is it? X, Y, Z, 2 power n minus 1, 3 power n minus 1 and 5 power n minus 1. Very clearly this is a sum of n terms of a GP, and that's clearly sigma 2 power r minus 1 will come out to be, r ranging from 1 to n comes out to be 1 into 2 power of n minus, how many terms are being added up? N terms. So 1 into 2 power n minus 1 by 2 minus 1. So that is matching with this. So this entry and this entry are matching, same. You will observe that sigma 3 power r minus 1, r ranging from 1 to n, again applying the sum of n terms of a GP formula, will match with this. That will be 3 power n minus 1 by 2, but you are multiplying by 2, so that makes it 3 power n minus 1. So these two match. Similarly, these two also match. So what do we have? The entire first row is coinciding with the third row. So when two rows are identical, we know that the determinant has to be 0. So we have the determinant to be 0. So the key formula that the key result that we are using here is that is when you have in a row some n number of entries, we can split, keeping the other two rows as it is, we can split the determinant into n determinants, or we can group these n determinants into one single determinant by adding in a particular row, keeping all the entries in the other two rows same. So that's what we have done here, and this was the step there. So the answer is 4. Answer is 4. Okay. Let's move to the next question. Question number 12. Determinant 1 1 1 first row, sin A, sin B, sin C second row, sin square A, sin square B, sin square C in the third row is equal to 1 by 8 r cube into A minus B into B minus C into C minus A, 8 r cube into A minus B into B minus C into C minus A minus B into B minus C into C minus A, and 1 by 8 r into A minus B into B minus C into C minus A. Now actually here ABC, capital A, capital B, capital C are angles of the triangle ABC, and ABC are the sides opposite to the those angles, and this capital R is the circumradius of the, it is understood from the question there, capital R with reference in this reference we can assume that capital R is the circumradius. Now what is the relation here between the side and the angle? We use sine rule. Use sine rule. What does the sine rule say? A is equal to 2r sine A, B is equal to 2r sine B, and C is equal to 2r sine C. So here the second row, since all the options are in terms of the sides, so we will have to convert the angles part into sides. So how do I do that? Sin A can be replaced by A by 2r. This implies sin A is A by 2r. Okay, so we will do that in the entire row. Row 1 is of course not changed, 1 1 1. Second row we have A by 2r. Can I take out 1 by 2r common here, and we have ABC. Third row has A square by 4r square, B square by 4r square. So we will take out 1 by 4r square common, and we will have A square, B square, C square. Okay, so you know that it's one of the properties of the determinant. If every entry of a particular row is getting multiplied by some constant, we can pull it out of the determinant. So 1 by 4r square was pulled out of the third row, 1 by 2r has been pulled out of the second row, and now this is coming out to be 1 by 8r cube, and this is a standard determinant, A minus B into B minus C into C minus A. C minus A. Now how do you verify it? It's a simple thing to verify here. Look at this. If I put A equal to B, these two first row and first column and second column become identical. That means by putting A equal to B, the determinant must have been 0, which means A minus B would be a factor. Similarly, if I put B equal to C, I would have got the second and third column to be same. Which means that the determinant has to be 0. So B minus C must have been a factor for it. Similarly, C minus A. So it's clear that it should be in this form. Okay, and that's 1 by 8r cube into A minus B into B minus C into C minus A. Is this? That's the right option here. So the answer is 1. Clearly, answer is 1 there. Okay, let's move on to the next question. Question number 13. If ABC are the sides of a triangle ABC, let capital ABC we can assume, and the determinant A square, B square, C square in the first row, A plus 1 whole square, B plus 1 whole square, C plus 1 whole square in the second row, A minus 1 whole square plus B minus 1 whole square and C minus 1 whole square equal to 0. Then the triangle ABC is equilateral, the triangle ABC is right angled isosceles, the triangle ABC is isosceles. Fourth option is it's a scalene triangle. Now clearly we can make one observation here. If I put A equal to B, suppose you put A equal to B, you observe that the first two columns become identical. If A is equal to B, the column 1 and column 2 become identical. So I will get A square, A plus 1 whole square, here again A plus 1 whole square. I am putting B as A, and then we have A minus 1 whole square here and also A minus 1 whole square. What does that mean? It means that, and okay, C square, C plus 1 whole square and C minus 1 whole square. So it's clear that by putting A equal to B, we are getting the determinant to be 0. Why? Two columns are identical, therefore the determinant is 0. So clearly A minus B must have been a factor for it. A minus B is a factor for it. Or A equal to B is making the determinant 0. You are given the determinant to be 0. That means that we can conclude that A is equal to B. Similarly, B equal to C. If I put B equal to C, second and third columns become identical. So B equal to C can be a possibility. Similarly, C equal to A. So now if I put C equal to A, also we will have the determinant to be equal to 0. we can't conclude that all the three are equal. So by taking A equal to B or B equal to C or C equal to A, we are getting the determinant to be 0. So we can at most say that the triangle is isosceles here. Okay, and option is 3. Now, if t is any positive integer, delta t equals to determinant 2t minus 1 m square minus 1 cos square m square, mct 2 power m cos square m, 1 m plus 1 cos of m square, then the value of delta t, t ranging from 0 to m is equal to 2 power m, 0. Third option is 2 power m into cos square of 2 power m. Fourth option is m square. Now, t is actually given as a suffix there of this determinant. So, we have actually m plus 1 determinants starting with 0 there. Okay. So, that makes it here delta t 2t minus 1 m square minus 1 cos square of m square, and here we have mct 2 power m cos square m, 1 m plus 1 cos of m square. We wanted sigma delta t, t ranging from 0 to m. So, sigma delta t, t ranging from 0 to m. Again, we observe that the second column and the third column are independent of t. So, what is varying with t is the first column only. So, suppose we have x1 plus x2, y1 plus y2, z1 plus z2, even let us say x3, y3, z3, some alpha, beta, gamma and a, b, c. We can split this determinant into 3 determinants, keeping the other 2 columns as it is and writing in the first determinant x1, y1, z1, second determinant x2, y2, z2, x3, y3, z3. We can split this into 3 determinants with the first determinant holding the values x1, y1, z1 in the first column, alpha, beta, gamma, a, b, c, plus second determinant will also have alpha, beta, gamma, a, b, c, and will have x2, y2, z2. Third determinant will have x3, y3, z3, x3, y3, z3, and the other 2 columns being same. So, if you had n such numbers here, you could have split it into n determinants. Now, it appears that now these n determinants can be clubbed into one single determinant having, we can write this looking at from the right hand side, because these 2 columns are independent of the indexing variable here. So, we can club them into one determinant. So, what we do is we can take the summation over these xi's. Okay. So, we will apply that rule for this problem here. So, we can take the summation in the first column 2t minus 1, t ranging from 0 to m, and mct, sigma mct, t ranging from 0 to m, and sigma 1, t ranging from 0 to m. Now, this is m square minus 1 in this 2 power m. These columns, second column and third column do not change. Cos square of m square, cos square m, cos of m square. That is what you have in this determinant. Is coming out to be this. Observe that sigma 2t minus 1, what is that? If you started with 1 and went up to m, it would have been sum of first m odd numbers starting with 1 going up to 2m minus 1, and that we know that sum of first m odd numbers is m square. But you are starting with t equal to 0, that gives you a minus 1, so m square minus 1. What about sigma mct? This is sum of the binomial coefficients in the expansion of 1 plus x power m, and what is that equal to? 2 power m there. So these two are matching, these two are matching. What about this? Sigma 1 added up how many times? T ranging from 0 to m. That means m plus 1 times as 1 is being added up, that is matching with this. So now the first and second columns are becoming identical, therefore the determinant is 0, and the option, right option is answer is 2. Answer is 2 then.